Good afternoon or good morning, whatever the case may be. I'm Kirk Harmon with the Harmon Group, a structural engineering firm in Philadelphia. I'm also president of the Council on Tall Buildings and Urban Habitat Philadelphia chapter. I'd like to welcome all of you to our virtual program. We believe we're moving. There we go. Next. All right. So thank you to our sponsors, JB&B Consulting Engineers, Bala Consulting Engineers, Turner Construction, Langan, and the Harmon Group Structural Engineers. We have some upcoming programs in the works. So when we're able, we'll also go back to in-person meetings, but keep an eye out for our announcements in the next several weeks. The Council on Tall Buildings and Urban Habitat is the world's leading resource for professionals focused on inception, design, construction, and operation of tall buildings and future cities. Please visit ctbuh.org for more information on the valuable resources available from this international organization. You can become a member at ctbuh.org/get-involved. So now I'd like to introduce Jared Green, principal at Langan, who will serve as our moderator today and introduce the panel. Jared?
Good afternoon and good morning. Glad to see you all here, the Council of Tall Buildings and Urban Habitat. We wanted to let you know that a portion of the proceeds today will go towards an organization based out in San Francisco, the Bay Area, called Rebuilding Together San Francisco. Their goal is to increase mobility and safety for seniors and neighbors with disabilities, to also reduce social isolation with wellness checks and connections to resources. And they're also geared towards preserving affordable housing for San Francisco families. So our goal here is to focus in on projects for the built environment, high rises in particular, in the Bay Area, but also do something to give back to an organization that's helping with the built environment there. So again, if you want to be a part of some of the things that we're doing here at CTBUH in Philadelphia, we invite you to become a member. Again, we will have continuing education credits available for today's talk, and some of the learning objectives are presented here. Again, we're talking about building tall and going deep, what it takes to support tall buildings in the San Francisco Bay Area. The session will show the significance of soil, bedrock, and groundwater conditions and the effect of basement depth in determining the appropriate type of foundation support. We're highlighting 3 high-rise buildings in the San Francisco Bay Area on sites with varying subsurface conditions, each with a different basement depth and different types of foundation support. Various criteria that have been used to determine the acceptable performance of tall buildings will be presented. And again, here are the learning objectives for what you will learn through this next hour talk. Our speakers: Lori Simpson, PE/GE, is a senior principal at Langan Engineering and Environmental Services, and she leads the Oakland and Seattle offices of Langan. She earned her BS in civil engineering at Stanford University and her MS in geotechnical engineering at UC Berkeley. She's a registered civil engineer in California, Washington, and New York, and geotechnical engineer in California. She has been providing geotechnical engineering services for over 30 years, solving complicated geotechnical issues throughout the San Francisco Bay Area. She's on the board of trustees for the Deep Foundations, DFI, and serves on DFI's Codes and Standards Committee and Women in Deep Foundations Committee. Scott Walker, PE/GE, has provided geotechnical and seismic engineering solutions for projects throughout California, Southwest Montana, and Seattle. He earned his BS in civil engineering at California Polytechnic State University, San Luis Obispo, and his MS in geotechnical engineering at UC Berkeley. For the last 10 years, he's volunteered his time on the board of the San Francisco Geo Institute and led their role in the development of new guidelines for tall buildings in San Francisco. And now we will have Scott and Lori talking about building tall and going deep, what it takes to support tall buildings in the San Francisco Bay Area.
Thank you so much, Jared. I will get us started. We're going to talk about 3 individual projects, and when we talk about building tall and going deep, it's really a matter of to have these tall structures, what it took to get proper foundation support, and what guidelines were used to establish that. So these are 3 mini case studies, and we're going to talk about 3 projects in particular. They are all located pretty close to each other in the greater San Francisco Bay Area. For those that are not familiar, San Francisco is here on the left, and Oakland and Alameda are shown on the right. And so we start going from left to right with the NEMA. NEMA San Francisco is at 10th and Market. Then we have Oceanwide Center as we go closer to the northeast. And then we jump across the bay and we do the Atlas, which is in downtown Oakland. Now, comparing these buildings, or actually before I do that, it is earthquake country. So all of these projects are within about 8 miles of a major active fault. So we have the San Andreas Fault on the left and the Hayward Fault on the right, both active and capable of generating large earthquakes. And although not a major topic of today's conversation, the design and earthquake design of these buildings played a significant role in the development of their foundation alternatives. So each of these buildings kind of side by side now. First we have the NEMA, then the Atlas and Oceanwide going left to right. Heights, we have about 400 feet tall for NEMA and Atlas, and Oceanwide being a little bit taller at 650 feet tall. And stories, about 40 stories for NEMA and Atlas. Again, Oceanwide a bit taller. All the buildings are concrete. We've picked these buildings to be relatively similar in that aspect. And concrete buildings are heavier considering other building types, and so that's important in the foundation design. They also all have basements between 1 and 3 basement levels, and because of how those basements are oriented on site, we do have a little bit different foundation depths. Oceanwide being the deepest at 65 feet. So seeing these buildings side by side, these are all on the same, these are elevation views, all on the same scale, with ground surface about at the same spot. Here we see NEMA and Atlas again, about 400 feet tall, and Oceanwide being taller. We also see that NEMA and Atlas are combined with some mid-rise. So a combination of high-rise and mid-rise does create its own challenges when it's going to function as one building versus Oceanwide, which was essentially a slender tower that occupied the full footprint. And with that, I will pass it on to Lori, and she'll do our first mini case study. I think you're muted, Lori. Lori, I think you're muted.
The unmute is in a different location when you're in presentation mode. Okay. So we're going to start with NEMA. Let's look at the layout of the building. It includes 2 towers, one at 22 stories and one at 38 stories. The building is fronting on Market Street, under which BART and Muni tunnels are present. BART being our regional and Muni being our local public transportation. And you can see the layout of the tunnels on the right. Here's a section cutting through the structure. The project has a single level basement under the north tower, so that's the right side, and a 3-level basement under the shorter south tower. You can see BART and Muni tunnels below Market Street on the far right, and you can see those diagonal lines coming up from the tunnels. These indicate the zone of influence as defined by BART. The zone of influence is a 1.5 to 1 line drawn up from the tunnels. If your building lands within the zone, you need to take measures to make sure that you are not adversely affecting the facilities. The building has fairly high bearing pressures, particularly in an earthquake. Here are the bearing pressures at the the north tower portion and part of the mid-rise right along Market Street. So you can see the pressures are as high as 31,000 pounds per square foot under earthquake loading. Let's look at the subsurface conditions we have here. The site is underlain by dune sand, which is prevalent over a large portion of San Francisco. The dune sand is loose to medium dense and extends below groundwater. It is underlain by a marsh deposit that is comprised of loose to medium dense clay or silty sand and medium stiff sandy clay. So the dune sand below groundwater and the sand portion of the marsh have the potential to liquefy due to an earthquake. and the clay portion of the marsh can consolidate and settle under the building loads. When we go below the marsh, we have the Colma Formation, which is a dense to very dense sand. This layer is great for bearing, but you can see that only the portion of the building with the deeper basement, that's shown on the left side under the south tower, extends to the Colma. The taller north tower basement bottoms in the dune sand, which is not great for bearing because of the potential for liquefaction. Plus, we have the marsh deposit, which can settle under static loads and also liquefy due to an earthquake. So note that part of the mat bears within the BART zone of influence. So it's key to know that BART has a number of guidelines that need to be followed when building within the zone of influence. All are important, but I'm going to direct you to the last bullet, which indicates that the structure should not impose temporary or permanent adverse effects, including unbalanced loading and seismic loading. So we have all these issues and constraints, and fortunately we have some solutions. So the key issues being the poor soil in the dune sand and marsh deposit and the potential for liquefaction. So we need to get our building loads into that Colma Formation, and we need to improve the ground to mitigate liquefaction. The constraints are that we should not apply additional load onto BART. So we need to extend the loads below the zone of influence. We also have to limit vibrations, which generally means no driven piles. Ultimately, we concluded that deep soil mixing could be used to mitigate the liquefaction, support the building loads, and extend them into the Colma. And we can deepen the deep soil mixing below the zone of influence to further extend the loads. Also, it causes no vibrations. So deep soil mixing is the mixing of cement into the in-situ soil by the use of augers, paddles, or a cutter tool. It creates a cementitious mix of soil and cement that can have strengths of about several hundred PSI. So we developed a number of requirements that were needed to be met to achieve the desired mitigation and building support while preventing adverse effects on BART and Muni. But to prove that we would achieve the desired performance, we had to perform a lot of analysis to prove to BART that we would not be adversely affecting their tunnels. So here's a cartoon showing this analysis. It's a finite difference computer program, soil structure interaction computer program that we use, and it's called FLAC. And here's a cartoon of the program setup. So you can see the top of the Colma Formation, that's our bearing layer, in yellow. And the BART zone of influence is the bright red diagonal line coming up from the tunnel, which is the white circle. And our loads need to extend into the Colma and below the zone of influence. So you can see the dark red shows schematically the depth and extent of the deep soil mixing under the mat. The mat is shown in blue and the loads are the orange arrows. So we set this up to model the conditions, and we run the program with the existing conditions before we do anything, just to set the baseline on what the existing pressures are. And I don't expect you to really read this. This is just to show you what it looks like. And then we run it with the deep soil mixing, with the pressures on the mat, and we can compare the pressures that we get from these stress contours with the original stress contours to make our conclusions about our effect on BART. So ultimately, we were able to conclude that we had no increase in stress under the gravity load and only a 4% increase in stress under the MCE earthquake load. And we also showed that the deep soil mixing was not being overstressed based on the strengths that the contractor was going to target. And all these results were accepted by BART. So that was great. So let me just show you some pictures in construction. The upper left, it's the cutter soil mix tool. The wheels turn, and there are ports that inject cement so that the cement is mixed with the soil while the wheels are turning. On the right, the tool is in the ground and we're creating a continuous trench of the soil mixed with the cement. And then the bottom left, that's the final product. So they're cutting down to the final mat subgrade, and you can see the grid of the deep soil mixing that was created, which can now support the mat and extend those loads to the bearing layer. Okay, so moving over to Oakland, let's look at Atlas. So just to remind you, it's 400 feet tall, has 1 to 2 basement levels, and it's one of the tallest and heaviest high-rise buildings in Oakland. The subsurface conditions here consist of a thin layer of fill underlain by the Merritt sand. It's a medium dense to very dense sand layer, and this layer can be a good bearing layer and is used for support of a number of buildings in the area. The Merritt sand is underlain by the Alameda Formation, which is generally a very stiff to hard clay that is highly overconsolidated. Being overconsolidated means that this clay has felt significantly higher pressures in the past than it is currently under. This layer is hundreds of feet thick. So note on this section that it jumps from 60 feet to 410 feet. And so when you go all the way to rock, it turns out, we have over 400 feet of this clay, and rock is at about 450 feet below the ground surface. So the bottom of the mat was planned to be about 28 feet below the ground surface, just right there at the groundwater. And it's bearing in the Merritt sand, which, as I said, can be a great bearing layer, and a number of buildings in the area do bear in this layer. But let's look at the bearing pressures. So this shows the average bearing pressures across different areas of the site. And so here, this gives you a bit of the layout. The right area, that's about 2/3 of the site, that's the mid-rise, and those are average pressures about 2,500 PSF, so not super high. The left portion, that's the tower, and if you look in the middle area, that's where the core is, we have 12,700 PSF average bearing pressures. So, we have some fairly significant differential pressures from the mid-rise to the tower. And then even within the tower, we have some significant changes across the tower footprint. So, we first said, what if we used a mat foundation for support? The basement bottoms in the Merritt sand, and at this depth, it's dense to very dense and capable of supporting these loads. But we do have hundreds of feet of clay below. And even though that clay is over-consolidated, it can still settle under the building loads. So we needed to check the settlement. So first we used a program called Settle 3D to evaluate the settlement. I know it's a little hard to see, but what we show is in that orange area in the middle of the tower, we're predicting almost 8 inches of settlement under the core. And we go out to the edges of the tower portion, we're getting about 3 to 4 inches of settlement. So fairly significant differential settlement just across the tower mat. And then when we look to the right side of the page where we have the more lightly loaded mid-rise, we are only getting about 2.5 inches of settlement. So some significant differential settlement between the two portions of the building. So, when looking at this, the client and the design team did not consider this amount of settlement to be acceptable. So what to do? Well, we could design a lighter building. We could try deepening the basement to offset more of the building loads. Unfortunately, in that case, then the basement was actually closer to the clay, and we had less bearing, and we actually saw greater settlement. We can use deep foundations, or we could use a pile supported mat. So in the end, we used a pile supported mat, and the team developed a target settlement of 4 inches. So we considered a number of different types of piles to support the mat to control settlement, and ultimately concluded that the augured cast in place piles were the most appropriate. Those could be drilled through the dense sand of the Merritt, and they create no noise or vibrations, and they're relatively quick to install. And just to remind you, we do have these different load pressures across the site, which is an important consideration when it comes to determining the pile length. So we would need longer piles where the loads are highest to really control that settlement. So again, a fancy computer program was used to help analyze and determine the settlement using the various pile lengths under the tower portion of the mat. And we are only talking about a pile supported mat under the tower. The mid-rise could bear on a mat foundation just right in the Merritt sand. So this time a program called Plaxis was used. And just to show you a little bit how piles can be used to reduce settlement, this is just a simplistic version of how we analyze this. So what the piles do is they help spread the load with depth, thereby reducing the pressure and deepening the application of the bearing pressure. So when we look at the tower mat and we use different length piles depending on the bearing pressures across that mat, we can see that we're spreading the load to a wider sort of equivalent foundation at depth that helps reduce the pressures and deepen them into the layer to reduce the settlement. So in the end, our results showed that we were getting up to about 4.5 inches of settlement with very little differential settlement throughout the tower mat, and actually relatively little differential settlement from the mid-rise to the tower. So this was all determined to be acceptable by the design team. And actually there was a little bit more analysis that was done, which showed the predicted settlement was closer to 4 inches. This sort of strange orange section in the middle here is due to just some artifact of some overlapping layers that we had to work to kind of overlapping pressures that we had to work in the program to get rid of that overlap. We found that there was less settlement in that area. So let's look at some pictures in construction. So on the left, you have the rig installing the auger cast pile. And on the right, you can see these screens are in the cab of the crane. And this is the automated monitoring that the operator and our field inspector use to confirm that the piles are being installed to spec. And then after pile installation, the site was cut to mat subgrade and the piles were chipped down. So on the right, you can see that almost all the piles have been chipped and they're prepped to receive the waterproof, and the mat subgrade is ready to receive the waterproofing and the mat reinforcement before pouring the concrete. Okay, so now I'm going to toss it over to Scott and he's going to bring you back to San Francisco.
Fantastic. Thank you, Lori. Had to hide the unmute button so you weren't alone in figuring out where that was. So back in San Francisco, we're now going to talk about Oceanwide Center. We are talking about the Tower 2, which is the concrete building. In this rendering, you can see on the left, Oceanwide has a big sister, which is Tower 1, which is the steel structure to the right. And we'll talk a little bit about that and the marriage of those two structures together. So Tower 2 is again shown here on some modeling and elevation profile. Important to note is, because it's basically a tower over the entire footprint, even and it's a third taller, we have much higher bearing pressures. Average bearing pressures between 12 and 18 KSF, the heaviest underneath the core. The project overview in a nutshell does include these two towers. Tower 1, 65 stories, but quite a bit taller. It's an office building, 910 feet tall. And Tower 2, the one we're talking about today, 64 stories, concrete, about 640 feet tall. It is over 3 to 4 basement levels, 3 under Tower 2, with excavations of the mass excavation down about 65 feet. Important to note that even though these two buildings, one's quite a bit taller, in terms of massing and the decision-making process for foundations, very similar approach, and both buildings had a really similar average bearing pressures. So running through our subsurface conditions here, a few more layers than Lori had to talk about. The site's underlain by fill and dune sand in the upper portion, which were all being taken out, so they didn't play a major role. And that leaves us with Tower 2 on the left of this profile, bearing in marine deposits. Similar to the marsh deposits that Lori talked about earlier, they're pretty weak. So it's a mixture of sand and clay and organic material, potentially liquefiable and highly compressible where clay, and really not an alternative for foundation support in that layer. It is underlain by that Colma formation, the same formation that the first project was founded in, the NEMA project. Across our site is about 15 to 40 feet thick. It does consist predominantly of very dense sand. And around this project, there's dozens of buildings that are supported on this material. However, under our Tower 2, it's only about 20 feet thick, and it is underlain by lots of marine clays. So here we've got marine clays and the Old Bay clay. They are older deposits than the younger ones deposited prior to the last glaciation, but that doesn't mean that they had any glaciers on them. So they're only slightly over-consolidated. It means that the relationship between the pressures today and the pressures that they've felt in the past is about 1.2 to 1.6 times. It is a very stiff clay. And the Old Bay clay, which is the weaker of these two units, is about 100 feet thick. If we get close to its maximum pass pressure, it is a very compressible material. So compression ratios of about 0.3. And we knew early on that settlement control was going to be a major issue on this project that needed to be evaluated. Those layers are all over our Franciscan complex melange, which is a bedrock unit we have across the Bay Area. It is highly variable, mostly because it's been deformed through millennia of shearing and seismic activity. It's moderately to highly weathered, but really when it comes down to foundation support, it is relatively incompressible and excellent for foundation support, as we'll see. In this cartoon, if we applied this 12 to 18 KSF at where the mat foundation would want to bear, if we were considering a mat, we didn't need a lot of fancy computer modeling to tell us that we had too much settlement. We're predicting north of 12 inches of settlement and differential settlement according to the pressures across the building. So what do? We put it on drilled shafts. In this case, we couldn't really, our Old Bay clay is quite a bit weaker than the stiff and hard clays at the Atlas. And so even a shorter pile design kind of founding in these shallower materials would still have excessive settlement. So we took the loads all the way down to the less compressible or incompressible bedrock, and they were installed from grade, making them a little bit longer than their final product would need to be. We then went through and performed excavations to get down to the pile head to build the basements. So the foundation details in a nutshell, 28 drilled shafts, so not very many considering the size of the building. They were up to 315 feet long beneath Tower 2, making them some of the longest drilled shafts ever drilled in North America from a top drive design, or top drive rig. They were fully cased to rock. Some of those clays were so compressible that they wanted to squeeze during the installation process, and we needed to case them all the way to rock. They were 7.2 foot diameter in the soil, about 6.5 in the component rock, or in the Franciscan complex rock. And they were all interconnected on Tower 2 with a continuous 12-foot thick mat. Axial loads on each pile ranged from 13,000 to 18,000 kips. And many of these lengths, ultimately, their lengths associated with capacity, were driven by the earthquake and wind loading. Total cost just for the foundation installation was north of $12 million. So now that we've said we're going to go to rock, it should be no problem. We have no more issues, right? Well, now we have to figure out how that we're going to get capacities. And where we're getting a lot of our capacity is in this melange. It is a really sheared up rock, and it's made of strong and weak rocks together. And oftentimes the weakest part is at that transition. So we have, in some cases, it can be really hard rock, which is the sandstone, which is the gray wacky sandstone, really hard rock and difficult to drill. And then in other times, or most of the unit actually looks like the core on the bottom, which is essentially sheared up shale, pretty soft, pretty plastic, and very soil-like. You can see on the bottom of these sketches, these were taken from cores 292 on the top and 294 feet below grade. So these are really close to each other in terms of depth. So in terms of putting some of this material in the ground, it takes a lot of work to put in shafts to this depth. Malcolm Drilling performed this work as a design build contractor. And these are photos showing a BG50, which is a very large drill rig, as well as an oscillator installing the piles and casing. And just a glimpse of some of the tooling required to get through some of the harder rocks, including a roller core barrel and a progressive bit, just showing the magnitude of some of these elements. And for further scale, this is one of our field engineers that was out on site for many hours observing this work. He's about 6'3", and you can see this cage in the background. This is one of our test shafts. We did have a double reinforced cage in the top of each of these elements, and that was to account for lateral design for earthquake and wind. So in terms of what can we use, or what kind of capacities can we get out of these shafts? We did opt on bidirectional load testing, essentially because the loading was really too high for conventional top-down testing to be an economical approach. Bidirectional load testing is when you put in load cells and instrumentation inside the pile, and you push both up and down. Looking at that setup of what we used on this project, it consists of lots of strain gauges and telltales, as well as we used a multi-level bidirectional load testing approach here. And here's where both the red and green on the sketch on the left are interfaces where the load cells were installed. So this allowed us to mobilize different portions of the pile at different times. So first we start by loading the very tip of the pile and see what kind of end bearing we can get. And then we open up the green cell and we can move the lower portion of the pile. And then we close the one on the bottom, and then we can start pushing up on the upper portion of the pile. In total, it gives you lots of data. Here is just a few quick snips of what we see is on the figure on the left shows the movement of the pile in the upward direction above the zero on the left side, as well as, as well as the pile tip on the left showing the downward movement. If you put those two pieces together, you can develop the equivalent top-down curve, which is now just the marriage of all the data together, where they interpret what the pile head movement would be. And here we see, even though it's really little, we have a combined load of 26,000 kips on this pile, and an equivalent head movement of less than an inch. So that's good performance. I wanted to have some construction photos too. So this is Tower 2 excavation. And what we're seeing is we're getting down close to the bottom of the excavation, and we're seeing these drilled shafts being exposed. All the shafts were over poured with concrete to make sure we had good quality concrete at the planned pile top elevation. We then have to go to work and clean all these piles off. So this is a photo of the massive chipping effort that it took. This was 8,000 KSI or 8 KSI concrete. And so when you get down towards the top of these, you have to clean them off delicately so you don't chip the intact concrete below or break the rebar. The photo on the right is showing some of the waterproofing detail. We do have about 60 feet of head pressure here, so water's well above our mat excavation. And the waterproofing detail included pouring about 4 to 6 inches of epoxy over the top of it as one of the layers of waterproofing. Here's some fun photos of Lori and I inside the Tower 2 mat. See lots of reinforcing. MKA was the structural engineer for this building, and this is their design of the pile mat. Included this reinforcing. Took us some work to get in there. And so this is the photos of Lori and I. And for reference, I'm 6'2" on the right here, and I'm reaching up and I can't even reach the top rebar, and I'm standing on a double mat of rebar on the bottom. Some other challenges on this project were just too fun to pass up, even though that they're not a major topic of today's conversation. This shows an elevator pit. On the left, you see the piles ready to be chipped down. In the center photo, I'm standing in the bottom of that elevator pit, about 85 feet below grade. And I'm looking up at our neighboring building, which is a 40-story steel building just across a narrow street. So one of the challenges we had was supporting our neighbors and making sure they didn't move around too much during this construction. So bringing it back to kind of our summary and why each of these foundation types was picked for these buildings. So just a recomparison of NEMA, Atlas, and Oceanwide. So NEMA had the lightest dead plus live bearing pressures, but really high equivalent loads. And luckily it was supported, able to be supported on that Colma formation, which was really thick. It does have old bay clay at great depth, but was not really a player in the foundation design over at NEMA. And our target performance was really no load on BART and mitigation of liquefaction. Static settlement wasn't a major driver in that foundation alternative. At the Atlas, where we have 3 to 12 KSF for dead plus live bearing pressures and that very thick, very stiff to hard clay, that target settlement of 4 inches was the main driver in developing the appropriate foundation system here. Lori talked a little bit about basement depths. Oftentimes, adding more basements and taking some load out of the ground can be beneficial, but if you do have a compressible layer, getting closer to that layer can have unintended consequences. And then ocean-wide, dead plus live bearing pressures of 12 to 18 KSF. And really the main driver was, the compressibility of that 100-foot old bay clay layer. We were targeting less than 4 inches of settlement as an overall approach. And we ended up with a settlement far less than that by going with the drilled shafts socketed into bedrock. So in terms of target, total, and differential settlements, what should projects do? As we've talked about, the foundation design really is going to be orchestrated or focused on or controlled by your subsurface conditions, as well as your building loads, and that's both magnitude of building loads and distribution. If you have a very unbalanced loads, that may result in unbalanced settlement performance. The depth of excavation, and then the performance criteria. And so that can be lots of different items. In terms of controlling settlement, uniform settlement of just a building by itself usually isn't so bad, as long as it goes straight down. Obviously, tipping is not so great for tall structures. No one wants a tipping building. And then differential settlement where one part of the building is settling significantly different than others, of course, should be avoided. So how does a project team determine the performance criteria? One thing to note, once you decide to put a building there, zero settlement is never an option. So the geotechnical standard of practice for deciding what settlement is appropriate is really not well defined. And significantly differs based on geography. For example, LA has some building code language that really wants to limit settlement of 4 inches, and that's a static plus seismic settlement. However, in Miami, where there's very different soil conditions, it's not atypical to be predicting more than 12 inches of settlement and generally be acceptable. In San Francisco, recently there's a new guideline published in 2020 that focuses or suggests that 4 inches is the maximum predicted settlement. But there's an asterisk there, and it says, unless it's a very well vetted design and gets peer reviewed and everyone accepts that it's acceptable to do more than that. In the Bay Area, there's many tall buildings that have been designed for 4 to 6 inches of total settlement. And really the focus has been, and appropriately so, control of differential settlements. A typical target is something like a 1/2 inch of differential over 50 feet. One thing that you don't want to do is be on this list of notable leaning buildings. So this is just some historic leaning buildings that are all performing well, essentially, or in use today, except for the Tower of Pisa, perhaps. But it's not good to be on that list for a new building. So how does a team go about figuring out what that performance criteria is going to be? Of course, it's input from the entire team. And structural and architectural performance should play a major role in that. Building envelope oftentimes has certain limitations that need to be evaluated. And we've seen, significant energy spent on making sure buildings are accessible, and whether that's getting in and out of that building or things like elevator performance. Oftentimes, tall buildings are in urban environments and have neighbors or nearby structures. So your building's performance, it's not usually just your building that's going down. We saw on Lori's slide how the depth of influence can spread out underneath some loaded structures. You do have to make sure that you're not adversely affecting those neighboring buildings. And then you have the perception of the public. Recently, there's been much more attention paid to settlement of structures and tilting of structures. And lots of folks are asking questions, whether they're investors or buyers of buildings, are appropriately asking questions about how buildings are being designed today. The geotechnical engineer's role, from our perspective, is always to come up with the least costly solution that really meets the desired performance. And so talking to getting the whole team on board for what that performance criteria should be is a great starting point. In all of these case studies, a mat foundation was considered as one of the most likely or preferred options because of the low cost. However, the predicted settlement was too high, or the other performance metrics, in the case of NEMA, really couldn't be met with that approach. And so we ended up with the foundations that we discussed today. With that, that includes our formal slides and portion of our presentation, and we wanted to make sure we left time for questions.
Excellent, excellent. Thank you so much. And there definitely are questions here. And if anybody else has questions, feel free to put them right in the chat. But we'll start with, let's see, Dylan Centella says, considering the liquefaction potential of the first site shown, so that was NEMA, were you able to observe liquefaction or any significant strength loss due to excess pore pressures when the simulations were being completed?
Well, so we didn't do any type of load testing, and the analysis we did was more for stresses. So we didn't perform any dynamic analysis in the computer programs that we used. So.
Okay, thank you so much. And then there's a question here from Filippo Mosabrio. He says, why were the auger cast in place piles installed at a higher grade compared to the mat subgrade? So Scott, you touched on this a little bit, but maybe you could flesh it out a little bit more.
I think that's Lori.
Yeah, actually, that's the atlas.
Okay.
So we were getting close to groundwater, and the owner and the contractor wanted to drill completely in the dry on a stable ground. Plus, we didn't want to get all the way to the mat subgrade and then run all these rigs all over and disturb the subgrade, because the low rise or the mid rise portion was bearing directly on a mat. So it was important to keep the integrity of that. So they stopped, I want to say maybe 5 feet above final grade to install the piles, and then from there, chipped them down.
Excellent. Thank you. And then we have an anonymous question here. Who is the general contractor on the Oceanwide project in San Francisco? Also, who did the structural concrete and rebar work? So we're looking for the cast of characters here.
Okay. The general contractor was actually a JV between Swinnerton and Webcor. And I'm not sure who did the non-structural concrete. MKA was the structural engineer for both buildings.
Okay. Excellent. Excellent. Feel free to put more questions. Anybody else that's out there, I'll ask a question. For the Atlas project, I saw that you buried in so the bearing strata was demerit sand. And it looked like the bottom of mat was nicely tucked above the groundwater level. I was curious to hear if that was coincidence. Was it something that was driven by the geotech? I'm curious to hear how that worked out there, because that's nice when that happens.
Yeah, it was coincidence. We were close enough that we still needed waterproofing, but it was nice to be above it, to be working in the dry and have less issues with water to deal with. But it was just coincidence. We did consider a number of different basement depths to see if we could have less settlement with a deeper basement, or if there was some benefit of having a shallower basement. And in the end, this was programmatically what worked. And because it turned out we needed a pile supported mat anyway, then it didn't matter to go deeper or shallower.
Okay, great. Thank you so much. Bidirectional test. Can you walk us through just a little bit? How often do you see bidirectional tests in the Bay Area? Is it something you see on every tall tower? Select tall towers, and then who brings it up? Is it the geotech? Is it the structural engineer? Is it the foundation contractor? Like, how do you end up with one of these very expensive sacrificial tests on a project?
Great question. I think bidirectional testing, although it does take a lot of preparation and time, ends up being a cost-effective approach, because the idea of trying to do a top-down test where you are going to resist 26,000 kips is really difficult, actually, to build a structure that can resist that load. I would say, every tall tower that I know of that's gone to a full-length drilled shaft or drilled system to rock has done a bidirectional load test. There are some elements of the building code in terms of factors of safety that you want to be able to take when working with a deep foundation, that you should have site-specific testing that can verify the capacities that you're estimating. So that's a reason to have a load test in the first place. And once you're putting in something that's on the order of 300 feet long, bidirectional is the way to go.
Okay, thank you so much. Here's a question from an anonymous attendee. For Oceanwide Tower 2, if the settlement criteria was 4 inches, was a load share between the mat and deep foundations considered?
I think once we went to a deepened foundation system, we looked at doing some type of pile supported mat and load share. Unfortunately, the materials present right below the mat really were too compressible. So once you start making your shafts long enough that they're touching rock, they're going to start picking up all that load. And so an option was we could put in more elements that are lower capacity, which are almost as long, or we could put in larger diameter, larger elements and pick up all the load. And really the idea of putting in several hundred elements in that same footprint versus just 28 shafts, it made sense to go with much higher capacity single element reactions there with the large shafts.
And one thing I'll tag on, I didn't make enough of a comparison with the Alameda clay that we had at the Atlas versus the clays that Scott spoke about at Oceanwide. And Scott went into great detail about the overconsolidation there, where it was like a factor of maybe 1.2 to 1.6. Over at the Atlas, the overconsolidation was on the order of 3 or 4 times the current pressures. And it amounted to, we could add up to 10,000 PSF without getting into virgin consolidation. So we did have a lot of load to play with and be on the part of the curve when we look at consolidation that's a much lower amount of settlement versus, the ocean-wide projects. Once you put, just a little too much extra load on it, you'd be on this part of the curve where you get a lot more settlement. So very different clay conditions.
Got it. Thank you so much. Now, when you're looking at these shafts, it looked like you have a shaft really coincidental with each column location. What type of plan dimension tolerances are acceptable? I mean, is this like what's acceptable in plan?
Yeah, I mean, because these elements were installed from grade, the tops of the piles are actually 65 feet down. And so the installation of that really heavy, it's a 1-inch steel casing down, in this case, it went all the way to rock, but oftentimes it would be at least into the Old Bay clay. One of those was to control the plan location of those piles when we got down to grade. They did have a 3-inch tolerance to play with in terms of pile location, or maybe, actually, it may have been 6. However, they were never close to that. That really stiff 1-inch casing was able to get them down to, less than I think the biggest was like 1.5 inches. So very good performance.
Awesome. Yeah, it's a lot of money going in the ground at that point. So you want to make sure it's going to be worthwhile once it's there.
I forgot to mention, each of these shafts takes 45 trucks of concrete.
Yikes.
So, yeah, a lot of money going into each shaft.
That's impressive. Thank you for context.
And how many days to install each one from start to finish?
Thank you, Laura. I forgot to mention that too. Each shaft was a 3-day construction process, and that's 3 days working 24 hours a day.
Wow. 24
hours a day, 6 days a week. So we had to pour every 3 days when they were doing well.
That is wild. All right, we got a question here from Blair Rushing. Were any other types of deep foundations other than drilled shafts considered for the ocean-wide project, considering the depth of bedrock?
Yeah, there were one other type was suggested once we decided to go with larger, heavy, high capacity elements. LBEs or load bearing elements, also called barrettes, were considered and were priced through construction. Ultimately, drilled shafts were selected, but barrettes were on the table all the way through kind of final contractor selection.
Okay, excellent. And then Blair also asked, in addition to bidirectional tests, were other types of integrity tests performed for quality assurance during the drilling of the shafts?
So yeah, we did have a full suite on our initial tests. Thermal integrity testing was performed, as well as crosshole logging. Ultimately, crosshole logging was used on all of the production shafts, and that's a methodology where essentially you test the speed of reaction of the concrete just to make sure you don't have any weak areas or inclusions inside your concrete. We did have concrete, essentially as these shafts were cast, the concrete was poured to be 20 or 30 feet above the interface of the casing as the casing was withdrawn. And because we had that significant overburden at the end, we were able to maintain that all the way through the production shaft length of the pour.
Okay, excellent. Thank you. A question here from Professor Hassam Yazdani. Great presentations. Aren't dynamic and liquefaction potential analyses required for tall buildings in the Bay Area?
I think the answer is yes. In terms of liquefaction mitigation and liquefaction triggering, absolutely, pretty much every building needs to be assessed for potential for liquefaction. I think what Lori was talking about was like a fully dynamic modeling of that liquefaction. That's what wasn't performed in that final condition. Lori, I don't know if you want to add to that.
Yeah, I mean, our soil structure interaction analysis was only a static analysis, and that was just it was static and pseudostatic. So we took the static loads, we took the seismic loads, but applied them just as a pressure. And we did not do a full dynamic analysis running, the ground motions through the analysis. It's not necessarily required in that type of analysis. Every project, of this type would have site-specific response analysis performed. I believe anything that's performance-based design, you'll do a whole suite of time histories. I mean, there's a lot of analysis that goes into each of these tall buildings. And now that San Francisco has issued this guideline for tall buildings, for the geotechnical, analysis of tall buildings, then it will, make sure that a similar amount of analysis gets performed on each of the buildings.
Excellent.
Yeah, those guidelines include 2 geotechnical peer reviews now for each tall building in San Francisco.
All right. And what's the trigger for tall?
240 feet.
Got it. All right. Question here. Thank you for clarifying. Question here from Daniel Tracy. What steps were taken to prevent undermining the adjacent buildings' foundations in these projects?
Well, I can speak. So Atlas was lucky that it was an entire city block. So we had no neighbors, which was great, made life a lot easier. At NEMA, we had one neighbor to the west, and it had actually a very deep basement. So its foundation was below the depth of any of our basement levels. So we didn't have to worry about undermining those. In terms of any of the streets, shoring systems were installed, and each one had different shoring systems depending on whether we were below water or what the soil conditions were. We didn't really talk about shoring in this, in this presentation, just for time.
Okay.
And then on Oceanwide, we had quite a few neighbors, and lots of time was spent, paying close attention to their foundation systems, as well as the performance of that shoring system. And in our case, we had the same tooling that Lori showed for using the ground improvement, the DSM. We had very deep, continuous, DSM mixed walls all around the Oceanwide project, and those include going up to 140 feet deep and getting well into the Old Bay clay. And essentially, those were installed before any of the foundation elements to essentially isolate our neighbors from any disturbance we'd have on site, or protect them from erosion or loss of soil.
Excellent, excellent. Question here, anonymous attendee. Are third-party special inspections required for concrete core sampling, such as core breaks?
Yes. You know, for ocean-wide in the drill shafts, there was this whole suite of special inspections, some of them being geotechnical that we covered, and some of them being structural, so rebar, concrete breaks, as well as the in situ, you know, crosshole logging I discussed. Each of those was included.
Okay, excellent. And then there's a question here. Are as-builds generated for all mat slabs?
I'm not sure. Yeah.
I mean, I don't know. I assume so. I assume they, you know, survey the bottom of mat, the top of mat.
Kirk shaking his head.
It's a good question.
Not
It probably depends.
geotechnical. Once the mat's poured, we're out.
Yeah, once we inspect that soil, we're good luck, guys. Go pour it. We're done.
Nice, nice.
I was just shaking my head because when the mats like that, when they place the reinforcing steel, and there's no way they're doing a as-built of that volume of steel at that depth.
Yeah.
All right.
You just count the bars. If they're all there, you're good to go.
There you go.
Got another question here from Professor Yazdani. It says, what factors did you consider when designing the configuration of the piles, especially as it relates to soil pile structure interactions?
So maybe that's for ocean-wide.
Yeah.
Ocean-wide essentially tried to put the piles where the load was. So essentially piles around the core, piles below any individual column. And then in terms of group effects, we actually modeled each entire foundation system holistically. So we did use, you know, a relatively simplified program called Group to evaluate what the group performance in lateral would be. And then we used simplified methods for any, you know, axial interaction. But essentially the piles were far enough away that they didn't have axial reductions in terms of capacity.
Okay, excellent. Yasima, Napoleon has a question regarding the subsurface exploration for these three projects. And she wanted to know, was any geophysical testing or instrumentation done? If we could talk a little bit more about those explorations.
Uri, did you have any?
On Atlas, we did perform downhole seismic logging to, you know, measure shear wave velocity in the different soil layers, and that, you know, feeds into our analysis of site class and, you know, helps us with our site response analysis.
And ocean-wide was similar. We had two downhole shear wave velocity measurements. You know, unfortunately, many of the surface techniques that we would have potentially used either don't go deep enough. We knew we were going to have 65+ foot deep basements already, or weren't actually accessible because our building, you know, our site at Oceanwide was covered with buildings. You know, some low-rise old buildings that were demolished in between when we performed the majority of our exploration and when the buildings were constructed.
Okay, excellent, excellent. Well, thank you so much. Looks like we got through all the questions. I don't know if anybody's feverishly typing right now. We'll give a few moments before we close out here. But thank you so much for your presentations and thank you for fielding the questions. Kirk, I'll hand it over to you to close us out.
Yep, as soon as I find that unmute. So thank you everybody for attending. Like I said, keep an eye out for future programs, and thank you Lori and Scott so much for what I found to be really interesting, but I'm a structural engineer, so that's why.
Our pleasure.
Yeah,
So
thank you so much for
everybody.
having us. Bye-bye.
Bye
All
all.
right, have a good one, everybody. Thank you for being here.